So 3.1 is an interesting section. It's an important section. So 3.1 is on what's called linear models. So linear models. So linear models. By the way, did I give you all extra credit for this for the test? Did we talk? Was that this class? Yeah. I gave you extra credit?
No.
Yeah, this is
You gave everyone 1 point.
No. I mean like an extra credit assignment. I didn't give you that.
No.
Oh, I didn't give you that?
an extra credit.
Do you want one?
Yeah. Hell yeah.
Yeah. Oh, I'm sorry, I forgot to give it to you. My other class has it. That's not fair.
It has to be at least 5 points.
Yeah, I know. It is. It's 5 points actually. It's 5 points if I don't have to. Yeah. Okay. It's exactly 5 actually. Good. We don't have to edit it file. Yes. Okay. Good. So I'll upload it tomorrow or tonight if I'm feeling motivated, and it'll be under resources. And I'll let you know when I make the test to find it. And it's 3.2. The extra credit problem is from 3.2, which is nonlinear models. That's why I'm talking about it. And the answer's in the book. Okay? You just gotta look in the book. Except it's about zombies, and in the book it's about the flu. So I changed it to zombie virus. Okay. All right. So 3.1 is on linear models. So very brief notes. So growth, and then we're just gonna do a problem similar to what you can expect. Growth slash decay, so like exponential growth, exponential decay, can be modeled. This is what DEs are used for. This is one application of them. Can be modeled by the initial value problem, okay? And I'll explain what this means, what growth and decay mean. dx dt, so dx dt equals kx, where the initial condition would be x of t naught equals x naught, equals x naught. Let me pause here and explain this. So x could be anything. So for example, oh, by the way, what does this mean? This means the rate of change of x is directly proportional to x. That's how you say it in like proportionality terms. Let's say x is the amount of bacteria in a puddle of water. So the rate of change of the bacteria is equal to some constant k times the amount of bacteria. If x is the amount of bacteria, the rate of change of the bacteria is equal to k times the amount of bacteria. You could solve this. This is separable. You would divide by x and multiply by dt. There's a couple homework problems that involve money, so like compound interest, stuff like that. There's a couple of them that involve maybe bacteria, so exponential growth. There's a couple that involve exponential decay. So you have to know what half-life is for that. Do you know what half-life is?
It's a video game.
It is a video game. I've never played it. So like if you have 10 grams of mathium and the half-life is 1,000 years.
It's used for radiation.
Yeah, so after 1,000 years you get half. So if you have 10 grams and the half-life is 20 years, right? After 20 years, how much do you have? 5. After 20 more, how much do you have? 2.5. Okay, so yeah, that comes up in one of the homework problems. I'll leave that to you, right? So there's a couple homework problems with that. There's a couple homework problems with compound interest. So what do you need to know for your exam? It's something else. It's not this one, okay? It's Newton's law of cooling. So let's do that one. So Newton's law of cooling. Newton's law of cooling. Newton's law of cooling. So Newton's law of cooling says the following. So it says the rate of change of temperature, so big T is the temperature, okay, with respect to time is directly proportional to the difference between the temperature and the temperature of the surrounding environment. And I'm going to write that down in words. I'm going to like tell you what everything is. So this here is the rate of change of temp. Okay, that's the rate of change of the temperature. That's what that is. Okay, and K is your constant of proportionality. Okay, so is directly proportional to T is the temperature at time T. Yeah, I was going to get you guys, but I felt bad. But don't worry, we haven't done a problem yet. So this is all you need. I was like, oh, should I go get him? I'm like, no, it's just weird. Like, I don't want to like. And then Tm is the temperature of the surrounding environment. So this is temp, surrounding temp. Surrounding temp. So on the test, you'll have to write this down and you'll have to solve it. Okay, so please go through it and solve. We're going to do one now, right? So don't just memorize the answer. So, okay. Most people who study get the word problem right. You might say, why? I don't know. Right? But they do. Like, they'll miss the homogeneous one or the Bernoulli. Like, of all of them, the Bernoulli is the best one, right? But that's just how it is. It's just because I like it. Doesn't mean other people do, unfortunately. So that's Newton's law of cooling. So you want to memorize this for the test. And I guess now we can do a problem, right? We can do, I think it's number, I can't read my notes. I think it's number 3. You will. Mm-hmm. Number 3 from the homework. So let's do number 3. And I'll write it on the board. I'll paraphrase it on the board. So number 3. Nick, can you slowly read it to me?
No, laptop.
Oh, anyone have number 3? My computer's off, so like, anyone have it? You have it? Read it slowly. Okay.
A thermometer is removed from a room where the temperature is 70 degrees Fahrenheit.
Okay. Thermometer removed. I got you. Removed from room where temp. My handwriting suddenly got better. Look at that. Is so good. 70 degrees.
Yeah, Fahrenheit.
That's an F, right? No, I'm kidding.
And is taken outside where the air temperature is 30 degrees.
Okay, where temp is 30 degrees. Okay, where temp. Okay.
After 1/2 minute,
Uh-huh.
the thermometer reads 50 degrees. What is the reading of the thermometer?
Okay, so A. It's okay, reading after.
At 1 minute.
And then what's the second part?
How long will it take the thermometer to reach 35 degrees?
Perfect. That's probably what's gonna. How long? Okay, to reach 35? Perfect. All right, take your time, write it down. So we'll go through this carefully. So if you can, this is the only one you'll have to be able to do, right? Take your time. Take your time. Thank you so much. Extra credit. No, I'm kidding. Oh, hey, Luigi, guys. There'll be extra credit on the test. I'll take home. I'll upload it under resources tomorrow or tonight. It's from 3-2. I'll upload. My other class has it, so I thought you all had it. I guess I forgot. So, yeah, there's extra credit for every test, I think, if you want it. Actually, they already have extra credit for the second and third test. I already have it, so, yeah. Okay, so this is the question. We have a thermometer removed from a room where the temperature is 70, and it's taken outside where the temperature is 30. After 1/2 minute, it is 50 degrees. The reading at T equals 1. So, what's the thermometer at 1 minute? How long does it take to reach 35?
Is that half a minute or 1.5?
It's 1/2 minute. Okay. It's 1/2 minute. So yeah, so after half a minute. So after 1/2 minute. So yeah, so 0.5 or 1/2. Yeah.
Gotcha. I thought it was a minute and a half.
No, sorry. All right, so solution. So the first thing you do is maybe write down everything you have. This is the tricky part, I think. I have to really think. I don't want to mess up. So the thermometer is removed from a room where the temperature is 70. So the thermometer is the temperature of the room, right? So that's the initial temperature. That's T of 0, right? So T of 0 is equal to 70, right? Because that's where the thermometer is initially, right? And then it's taken outside where the temperature is 30 degrees. So it's it's colder outside, right? That's the TM, right? That's the TM. So TM, I always think this is like the hardest part. Like this part here, like the beginning for me, like, because I always get confused, like, is that the TM? No, it can't be, right? Because it's 70 degrees in a room, you take it outside, it's 30, so it's gonna cool down, right? The thermometer's gonna cool down. This actually models the cooling of the thermometer, like you can test, like with the thermometer. Or heating up too. Take a potato, stick it in the oven, it's supposed to work. I've never done it. After 1/2 minute, it is 50, so T of 1/2 is 50. Right, so these are our conditions. These are called boundary conditions because these numbers are different and they're both conditions on T. Notice there's no derivative here. These, together with this differential equation, it's called a boundary value problem. Right, it's actually called a boundary value problem. All right, so let's plug everything in. So we have dt equals k. We'll have to figure out k at some point, right? And then t minus tm, which is 30. Which is 30. I'm going to go really slow. 30. 30. And we're going to go through it carefully and just solve it, right? So on the test, like just go through it carefully and just, you solve it. Okay, so this is separable, right? So you divide by t minus 30, multiply by dt. So we have dt over big T minus 30 equals, multiply by little dt, k dt, right? Beautiful stuff, right? K dt. So just divide by this, and then multiply by dt. It's a nice application, right? I like Newton's law of cooling. It's an easy one to do. And then 3.2, the extra credit has like more complicated population problems and stuff. Like the zombie virus one, like you have a finite population. The question is, how long does it take people to get infected, and what happens? Does everyone die, like, or does everyone become a zombie? They do. They all become zombies eventually. So. Huh? Yeah, it is. Yeah. We're all zombies. All right. So it's kind of dark. Okay. To integrate this. This is going to be an ln, right? You let that be your u. So I'll skip that step. So ln, absolute value, t minus 30. We have to solve for big T, right? So this is going to be kt. And because the big T is in the ln, we know it's going to change, right? Stuff is going to change. So instead of c, I'm going to call it something else. Maybe c tilde. Yeah, who said that? Yeah, C tilde. Yeah, very good, tilde. I think we did this before. You can call it C1. I just like to use the tilde. Yeah, it's great. How do you get rid of the ln? What do you do to both sides? Do you remember? E, yeah, it's coming back. Yes, exponentiate. So this is like 2.2, right? So you get more practice for that too for your test. So it's good. It's a good problem. These cancel, right? The e and the ln. So you get absolute value, t minus 30 equals. So you have this. So this is really e to the kt times e to the c tilde, right? Because when you multiply these, you add the exponents, right? Recap from I think from last time, right? I think it was a good review in a sense, right? Even the linear, when we did the Bernoulli, it's like, oh yeah, like it comes back. If you're feeling fresh tonight, if you feel like you understood anything at all, go home and do it tonight if you have time, right? That way you don't forget, I know it's hard to do that because you get home, you're tired, you're hungry, you just want to take a shower. It's like, I got to work tomorrow maybe, life. Okay, so we want to get rid of the absolute value. When you drop it, do you remember what you always put? Plus or minus. Yeah, plus or minus. E to the c tilde, e to the kt. I know, I should go home and make your test tonight, right? If I'm saying that, right? And post the extra credit tonight, right? But
right?
I should be doing that, right? And I'm telling you to study, go home, do these tonight. I should make the test tonight, right? Hey, what can we call this? We just renamed this. What can we call it? Call it C. Yeah, absolutely. So T. I might make the test tonight. Probably not, but is anyone? Yeah. I don't think anyone cares. I'll wait till tomorrow. Let's call it C. And add the 30. So we get T equals 30 plus C times e to the kt. I'll pause here, let you catch up. Did y'all hear they're closing those Lucky stores? Is that true? Anyone hear about that? Yeah, I found out today. It's yeah, Lucky's. That's where I do all my grocery shopping. Sad. I'm hungry thinking about it. All right, so my stomach just hurt. So we're here. Any questions up to here? Well, Lucky's and all these are still good. Any questions? All right, now we got to use our boundary conditions, right? So I think it might be easier to use this one first, the 0 one, because that'll make the e go away. So let's use this one first. Okay, so we just got to use both and we have to find c and k, right? Then we can answer all the questions, and it's easy. So t of 0 is 30 plus c e to the 0. right? So isn't that just c? Yeah, I don't know why I got confused. And that's equal to 70, right? It's this one here, right? So this is 30 plus c equals 70. So that means c equals 40. So I'm going to plug it back into this. We have t equals 30 plus 40. If this is bothering you a little bit, the t, it's really this. It's really t of t. Right? It's the same thing, but we just write t because we're lazy. But it's the same thing. It's the same thing. It's just people being lazy, right? I mean, you're supposed to do that, but yeah. There's all kinds of stuff like that in math where like you're supposed to do something, people don't do it, even though it's like technically not correct. It just becomes like an accepted bad practice. Like, so people do it. It's like, yeah, it's worse than that. That's actually not that bad. Now we have to find k. So we have to plug in 1/2 for little t and set it equal to 50. So let's do it. So it'll be t of 1/2. This is 30. 30 plus 40 e to the k times 1/2. What do we set this equal to at this point? 50. Yep, 50. It's this one. It's the other boundary condition. Fun word to use, right? These are called boundary conditions because they're different numbers, right? Normally they're the same number, and like one's on t, one's on t prime, right? It's kind of cool. All right. So now we can solve for k. So subtract the 30. So you get 40 e to the k over 2 equals 20. It's really easy to mess this up. Every once in a while, a couple people will make mistakes. What happens if you make a little mistake? It's no big deal, right? If this, I mean, it depends how much work you should. If this is worth 30 points, you make one little mistake, it's like -2 or 3. A lot of times, it's an arithmetic mistake. Like people will, they'll subtract wrong or something. I'll notice it usually if it's that. But yeah, don't make mistakes. It's better not to. So this is 40. So we end up with e to the k over 2 equals 1/2, right? 1/2. 20 over 40 is 1/2. Right, it's 1/2. To get rid of the e, you can take the ln on both sides, right? So I'll put ln e to the k over 2 equals ln 1/2. These cancel, so you get k over 2 equals ln 1/2. Multiply by 2, you get k equals 2 ln 1/2. I'm going to circle that. That feels like really important, right? That's that. When I grade the test and you mess up, the first thing I look at is to see if you got the k right. It's just really easy for me to check that. So like, if you got the k right, that's really good. That means your mistake. A lot of times people get the k wrong. Like they'll have like a 1/3 or something. It'll just be slightly off. And then usually I can find your mistake. Now we take the k and we plug it back in. I'm going to come back to that board and I'm going to take this k and I'm going to put it back in here, okay? So I'm going to come back over here. So we have t, this one here, this t. So t of t is 30 plus 40 e to the kt, right? So it'll be t of t is 30, so 30 plus 40 e, and then k is 2 ln 1/2. So it's 2 ln 1/2. By the way, you can rewrite this entire thing to make the problem easier. I won't do it, but like you can bring the 2 up and you can use properties. You can bring the t up. It becomes an exponential function. I'm going to leave it though, but you could. You can get rid of the e here. Like you can do some math and get rid of the e. I won't do it. I'll just leave it. So that's not the answer, but that's like important. So I'm going to put that in a box. That's a 1/2, by the way. It's ln 1/2 t. Any questions so far on how we got t? Now we're going to answer all the questions. So the hard part is coming up with t. The rest of it's pretty easy. All right, there's 2 questions. We want to know part A. So reading at t equals 1. So the solution to A, even though I already wrote solution, but is t of 1 equals 30 plus 40 e 2 ln 1/2. You could probably do it without a calculator. You could probably bring it up and work it out, right? Because you're bringing the 2 up, you get ln 1/4. That becomes 1/4. I think, yeah. You want to try to do it without a calculator, or let's live large. 30 plus 40. No one says that anymore. Live large. Is that even a thing?
I think most Americans do that already.
Live large. I get it. Okay, these cancel, so you get 30 plus 40. Is that right? 1/4? Yep. Whoo! 30. What's 40 times 1/4? 10? That can't be right.
What? 7.5. Half of 15,
I got
yeah?
40.
Huh?
You said 30 times 1/4, yeah?
No. I said the wrong thing. Is that the answer? 40?
Yeah.
You typed it in? Anyone type it in?
Yeah.
30 plus.
No, I mean to the homework.
Oh.
It feels really wrong. It feels really wrong. I don't think it's 40.
Nah, I mean, it could be 40.
No, I thought it was a decimal. Like in my notes, it's a decimal. I feel like we messed up, and I'm going to give everyone a point.
Decimal after another 30 seconds from 70 to 50 and 50 to a decimal.
Yeah.
Oh, say that again? Oh, you're thinking, let's see, I didn't even.
That's right.
40 is within range.
It's within range?
Sorry.
No, you're good. No, it's good. So can you explain it again? Can you explain it again?
Well, I mean, just, so in 30 seconds, it went from 70 to 50.
Uh-huh.
So from another 30 seconds, it going 50
Went
to
up
a
40.
decibel seemed just outrageous.
Okay, so say it again. So 30 seconds.
It went from 70 degrees to 50 degrees.
How do you know that? Oh, from the condition, which I erased. Okay. And explain the rest.
So then the next 30 seconds, I found it hard to believe that it went from 50 degrees to point something.
Right. Yes, good.
Also, like, what I'm thinking is that, like, 70, like, if the outside is 30, and it came from 70,
Yeah.
and,
How
like,
are
you
we colder
cut
than the
that in half
outside?
and 30.
Yeah, right. How can it be colder than the outside? Well, it's the twilight zone. No. Yeah, good. So good. I've never gotten a whole number in this problem, like ever. Yeah, ever. It's always like some weird decimal, always.
So then, like, after 30 seconds, you could, like, cut the difference in half, so then after another 30 seconds, you,
I
like,
think
cut
we're
the
having
difference in
to-
half.
No, it's not linear though.
Yeah, it doesn't work like that.
Well, I mean, like,
Oh.
it was from, like, 70 to 30, so half.
It does this.
Yeah, so after
Yeah,
that
but it would
50, so
go,
after
it would
another
go
30
below.
seconds.
Yeah. All right. Let's keep going. Solution to B. Now, how long does it take to reach 35?
Oh, okay.
So how long does it take to reach 35 degrees? Any ideas?
Probably a little bit.
Yes. Wait, maybe not.
The answer is actually 2 years. No, I'm kidding. So you take this, So you take this, and you set it equal to 35, right? Because this is the temperature. So you have 30 plus 40. Yeah, we got such a nice answer, I got scared. Like, I'm like, well, it can't be 40. Like, so that's probably a good one for your test, right? So something like that. Now we have to solve for t. So subtract 30. So minus 30, minus 30. So that'll be 40. Oh, I'll put the minus 30. Minus 30, minus 30. These cancel, so you get 40. E to the 2. Again, I could have gotten rid of this e a long time ago, but I'm just being bad. And this is equal to 5. Divide by 40. Uh-oh, big numbers. We get e to the 2 ln 1/2 t. 5 over 40 is 1/8. 1/8. Makes me think of pizza. 1/8. There's like 8 slices of pizza usually. I'll take the ln on both sides. It's really bad. I should have gotten rid of that e, but it's all right. It's all right. We can just do things the wrong way or the long way. 2 ln 1/2. Wow, ridiculous, right? Divide by 2 ln 1/2. We get t equals this divided by this. So a lot of math there. So take the ln, these cancel. So we get t. All right, so we have room now. So t equals ln 1/8 over 2 ln 1/2. And so when you put this in your calculator, you want parentheses. I don't know what the answer is. Maybe someone can Tell me. How many decimals does it want in the homework? 2?
Is it 1.5 minutes?
No, we need decimals. Is it 1.5? That's what you got?
Yeah.
That's what you got also? Anyone else? No, not that I don't believe you guys, but
I mean,
okay. So it's just this. Did you put this in parentheses in the bottom?
Yeah.
Yeah.
It's 1.5.
Okay, 3 people say it must be true.
Like exactly.
How many decimals does it want? So did you do 1.50? Did I mark it right?
Oh, I didn't know those.
Oh. Anyone type it in yet? I'll wait. I'll wait. So to make sure it's right. I'm really bad if it's wrong. We still have 12 minutes. This is really good.
Yeah, that's right.
Yes! All right, so good stuff. So any questions on this problem? Any questions on this? That's not so bad, right? It's not so bad for a word problem. I think like the intermediate algebra word problems are harder, like when you have like those mixing problems, or like Joey works for 5 hours and John works for 10. You know, if they work together, it's just like, those problems are horrible. So yeah, Newton's law of cooling. So interesting. So after a minute and a half, it got to 35 degrees. No, it gets infinitely close. Yeah, there's an asymptote. If you look at, good question. If you look at this function, this number here, ln 1/2, is negative because the log function looks like this. This is ln x, or let's call it ln t, and this is the t-axis. And this is 0, and this is 1. So ln 1/2 is down here, so it's negative. So this is e to a negative number. So when you take the limit as t goes to infinity, you do get 30, right? Because this goes to 0, right? So it gets infinitely close to 30, but it never actually gets there based on
Close enough.
that we just call it 30. It gets infinitely close to 30, but it never, according to the formula, it never gets there. It's kind of a cool thing. Like in theory, I think, if you took like a potato, right? And so you have 2 things, right? You have the initial temperature. You have some temperature after like, a half minute or whenever. And then you have the temperature of the surrounding environment. So say your oven is, I don't know how hot ovens get, but like 200 degrees is probably not real. I don't know. And then your initial temperature is 75 because that's how hot it is in your house. And then you put it in the oven, and after half a minute, it's like 120 degrees. I don't know. Then in theory, if you have all of these things, in theory, you can model how hot your potato gets in the oven using this. So I've never done that though, because I care, but not that much. I don't know. I have other stuff to do, like I'm gonna go home tonight and like stick a potato in the oven. But you could do it. Like I believe that it works. I believe Newton, so I'll just believe him. But you could try it if you're interested, and you can, in theory, you can do it with everything. Huh?
Not all potatoes are the same, so it's not going to work every time.
Right. Not all potatoes are the same, but
Close enough.
But these conditions, this should tell you this changes based on the potato, right?
What do you do for like how much potato weighs?
Right?
The outside of the potato, not the inside.
Well, you stick a thermometer in it. Right.
It's like just bring a microwave or basically test it.
Yeah. Not all potatoes are the same, right? But I think
Yeah, the T1/2.
the T1/2 will change based on the object, I think. But yeah, it's probably not perfect. You're right. I know, you should try it and like, don't burn yourself. Come to class, my hand's a bandage. All right, let me turn this off.